Okay, hi everyone. So we're doing absolute value and absolute maximum values, absolute minimum values. We're quickly going to go over this. The f of c is a point. We have a maximum value if f of c, that y value, is bigger than every other value in your graph. And looking at our graph here, if we say our domain is only within the red, at b, f of b is our absolute maximum value because it's bigger than everyone. Look, it's bigger than everyone else within the domain, within that red domain. Absolute minimum refers to our lowest value here. And for us in this graph, we would say that's at C, right? F of C here. So that's lower than any other value in this whole graph. So that's what absolute means you are the dominant king. But if we look at some other keywords here, local max and local min, you don't have to be the favorite, but you have to be the favorite of your local community. And if we look at points H here, H within its local community is bigger than its neighboring partners. For local minimum, look at K. K looks like it's kind of in the middle, but if we only stick to what's between the red lines, it is a local minimum because he's shorter than its local neighbors. Okay, so local min, local max are important for us, and also knowing when something is the absolute max and absolute minimum. Okay, so these endpoint values are super important when it comes to talking about maximums and minimums, because if we have arrows that go on forever, right, this guy here goes on forever, that means we don't actually have a local max, because you have to tell me what that maximum value is. And infinity is not an answer, because I can always say infinity plus 1, and now that's the maximum. Oh, infinity plus 2. Now, infinity is not a number. It's more like an idea, right? A concept. Okay. So here is our next rule, the extreme value theorem. The extreme value theorem is really important for us because it is always going to be true. When you hear the word theorem, like the theorem of relativity, I guess. I don't know. No, that's the theory. Oops. Sorry, that's the wrong word. So theorems, theorems for us are things that we can guarantee. So in this idea here, if f is continuous, that means the function is no breaks, no stops, no jumps, okay? This graph is like a polynomial, just keeps on going, okay? Keeps on flowing on a closed interval. And we're saying between A and B, this guy has to be closed, okay? It has to stop, it can't shoot off to infinity. Then F has both a max and minimum value on that interval. Okay, now this is a promise to you, right? If we give a definite timeline, you'll always have a maximum and a minimum value on that. In our previous example, when we first started, we drew arrows that shot off to infinity. That is not a closed interval. That is from infinity to infinity, and that is not a closed interval. So here's my idea. If I go ahead and draw you a graph, and I draw you a closed interval from A to B, try drawing any graph from points A to B, pick a point, and ask yourself, is there any way for me not to have a max? So looking here, I'll call this 1 and call this 2. Don't we have a max and a minimum at 1 and 2? Right? We have to. What if I draw a graph that looks just like a stupid line between A and B? Do we have a maximum and a minimum? We do, right? Think of a graph that you've seen and try to break it. And what happens is you can't, because if I stop the graph at A to B, it never shoots off to infinity. You might say, Mr. Ko, what about the graphs that we did before that look like this? And we can say this is from A to B. But is this graph here continuous? Right? And not continuous. So it's almost like we fixed the race. We gave ourselves rules that we can't break. And because we can't break these rules, we always have this true statement. So they can always ask you, what is the maximum and minimum value if they close that interval? Because if it doesn't happen in the interior, these are interior points. Right? These happen someplace along the graph. They happen at the endpoints. Okay, they can only happen, it's only two possibilities, right? It's either going to happen on the inside or it's going to happen at the end.
But for the parabola, wouldn't the minimum point be in the interior and then?
Yeah, it's interior, right?
Okay.
And the maximums, let's say these are exactly the same value, right? Those happen at the endpoints. But there's no other points on the graph. It's at the interior, exterior, interior or endpoints, and that's it. And these are just the possibilities that they're describing. But there's no way to get around this. You can't break this rule. It's like I set up the game. You can't break the game because I set it up this way. Now, could you still have a maximum value even if, could you still have an absolute max or min even if there is no boundary? Yeah. So what if I give you guys a graph that's just a basic parabola? Okay, call this -2 at 0. Right? This is not bounded, so our rule does not apply. The extreme value theorem does not apply here. But does it mean it doesn't have a max or min? No, this one does have a absolute minimum. At 0, -2. That's my absolute minimum, but no absolute max. And that's okay because the rule didn't guarantee me a maximum. But if it's closed, it is guaranteed. Now, let's go back and talk about our relative max and relative minimum values. So, let me draw you one more thing. Just as an example here. If I draw you a graph that goes, we'll call this A, B, C, and D. Okay, A, B, C, D. So we're going to label this as, tell me which letter would be my absolute maximum value.
D.
D, right? And that's an endpoint, right? So D is my absolute max. What is my absolute minimum?
C.
C, because that's lower than anyone else, right? This is Oscar the Grouch. He's like the lowest place on Sesame Street. And we have local maxes and mins along here too. So a local max would have been B. This is a local max. And then A would be a local min. You might ask me, what about all the points in between? What are all these other points? Aren't these points special too? Answer is no. If we're looking for extreme values, none of the points in red are extreme. It's just on the way, right? If you're going from here to Vegas, these points are just on the way. Like you can think of your bladder. You hold your pee, right? And then you get to Barstow and you're like, and then your graph drops. And then on the way to Vegas, you hold your pee. You can't let your pee out any place else along your trip except where you stop, right? So these points don't matter to us. They're not absolute. They're not extreme values at all. Right? Now, one popular graph oftentimes we see is the one you'll see in the book, and they draw stuff like, it's just a long curve. And some parts are it's nice and smooth and some are not. So we're going to give ourselves, we'll just copy this down. A, C, E. I'm just copying the book's example. Okay, from A to B. Okay, so I want you guys to look at point A. Would you call this absolute max, absolute min, local max, or local min?
Absolute minimum?
Absolute minimum, yes. Because this value is lower than anyone else. But you could also call it, if you want, a local min. In addition to it, this is also a
We can't hear you, Mr. Ko.
so not
Your voice.
okay. So not only is our point at A an absolute minimum, it can also be considered a local minimum too. So these are okay. All absolutes are also local. Think of the word local. You are still locally worse, in this case, minimum, than your peers, right, your neighbors. Okay, let's look at point C. Point C is, what do you guys think? Local max, local min?
Local max?
It is a local max because it is not the Mount Everest. It is local max. Okay. And here's something I want you guys to notice. The slope is going to be 0 here. And this is something we're kind of jumping to. But the tangent line slope of our interior points are actually going to be 0. And that's one of the ways that we discover if something is a local max or a local min, is that the derivative is going to be 0. The slope is positive, 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 negative, negative, negative. How does the number go from a positive to a negative? It must cross through the border of 0. That's something that we're going to get to a little bit. And then E is going to be a local min. See, look at D here. Is D a nice curved point, or is it a little bit sharp?
Kind
Try
of
to draw a
sharp.
little bit sharp. So is there a derivative at corners? Remember this rule?
No.
No, there is no derivative at corners. So being an extreme value, it doesn't matter if you're differentiable or not. It just matters that you're continuous. So as long as there's a bridge across, we don't care. You are an absolute max there. There's also a local max, but not differentiable. Which is okay for us. We just care that it's continuous. And the last point, B, is this anything at all? B? Anyone want to risk it?
Local
Could it be a
min?
local min?
Yes, it is a local min because it is still less than its peers. Okay.
So how do you quantify like how far you look along the line for local?
They have to give you the endpoints because if they don't tell you where to stop, there's nothing to tell you that's like point B. So they have to tell us a starting and a stopping point. If I give you a graph that, again, just like this parabola here, and I don't tell you a domain except negative infinity to infinity, there is no stopping point. But if I cut it from A to B, these are now endpoints that we can describe as local maxes. Because if it keeps on going, we can't say anything about it. There's always a point that's bigger, so it's not anything till you decide to cut off the line someplace. Good question. Okay, these can also local extremas, or extrema, sometimes you can call it extrema, can also be called relative extremas. right? Local and relative, because it's relative to the near values, the values that are right next to it. Now, what we just showed you guys was a nice picture of it, and I talked about the slopes being 0. Now we have a new rule that applies derivatives into this, and our rule is local. Here's our rule: local extreme values. How can we look for local extreme values? And it doesn't seem like it's a follow through from this, but I want to find them. I want to find where my maxes and my mins are. And there's actually a cool thing. Okay, so if we have a local max or local min inside a function, we can determine that by this rule. So local max or min inside a function by f prime of c is equal to 0, where c is in the domain, c is inside the domain. Okay. What we're saying is that if you have a derivative that's equal to 0, that might be a local max or a local minimum. Now, let's do a dumb problem. We all know what x squared looks like, right? Y is equal to x squared. We all know the parabola has a local minimum at 0. Oops, other way around. X equals to 0, right? And at x equals 0, the point is 0, 0, right? And that's the lowest point on this graph. We are all okay with that from algebra 2. But I'm going to prove that to you using our rule that we just said. So we take the derivative f prime of x, which is 2x, right? Take the derivative of it, and we set it to equal to 0. We set it equal to 0. Set that sucker equal to 0. When we set equal to 0, what value of x would make that 0? Divide 2 on both sides. X would equal to 0. So we know the location of my critical point. And this is what we're going to call it a critical point. Critical points are when the derivative is equal to 0. We're going to give a little caveat to it. It's going to be equal to 0 or does not exist. But let's go ahead and start off with just our critical point is equal to 0. Now, here is the problem with this. By us taking the derivative alone doesn't tell us if it's a max or a min. It just tells us that something is there. Like when you smoke, does it mean there's a fire? You just know that there's something wrong. So when I set a value equal to 0, we know that there's something wrong, and we can then go explore that idea. Okay, so that leads us to the idea of critical points. Critical points, let's go through this definition. Critical points are when f prime is equal to 0 or when f prime does not exist. Now, why do we have to include these two ideas? F prime is 0? Sure. Let me show you that. If the slope, is 0, that's a critical point. Yeah. Okay. But also when it doesn't exist. So let's look back, scroll up real quick. Remember how we mentioned that the derivative doesn't exist here? That was an absolute maximum. That was the extreme value. So if there are little corners, extreme values could exist there, but the derivative isn't 0. So we have to include that little note. So critical points are where extreme values can happen. Okay, critical points are where extreme values can happen, but they might not. Okay, they might not also. So let's come up with a problem. Let's say this. Find the absolute extremas of, let's do Let's do 3. Y is equal to 3x squared plus 2x. Okay. Now, do you want to graph this graph? I mean, we can do that right now, no problem, right? But it's going to cost us time and work. So the rule in calculus is that I can find the extreme values of this by just looking for its critical points. 1, look for critical points, which is f prime of c equals to 0. So just set the derivative equals 0. Let's take the derivative. 6x plus 2 is equal to 0. Okay, 6x plus 2 is equal to 0. Solve for 0. So solve for x. Minus 2 minus 2. 6x equals to negative 2. Divide by 6, divide by 6. X equals to negative 1 over 3. So now that we have at least this part, we can now plug it in and look for my y value.
Where did you get the 6 from?
I took the derivative of x squared.
Um,
So we're going to plug in 3 times negative 1/3 squared plus 2 and 1/3. And that's going to be 3 over 9 plus 2 over 3. 1 over 3 plus 2 over 3 is 3 over 3. And that's going to be 1. So we have an extreme value at
It's
negative
not-
1 over 3. Or
Mr.
critical point.
Poe.
Minus. It's
Yeah,
Oh,
not.
Mr.
minus?
Poe, why is it
Oh,
not
shoot. I
negative?
meant, yeah, you're right. That was a minus. So that's a minus. That's a 1/3. Thank you for catching that. A 1/3. That's it, 1/3, right?
Negative 1/3.
Thank you. Wait, negative or positive? Positive, right?
Negative. It's 1/3 minus.
Oh, shoot, you're right. Dang it.
It's all good.
Minus 1/3, 2/3. That's why it's negative 1/3. Sorry, I skipped a step. Now, the problem is, so we look at our point, negative 1/3, 1/3, and this is a critical point. We don't know yet if it's a maximum or minimum value, okay? We don't know yet. But if you know what an x squared graph looks like, doesn't this graph point upward, right? If it points upward, that means the critical point, the only critical point is a minimum. This is our absolute min. Or we can say it's a local min first, and then we can then declare it's an absolute minimum because it is a parabola facing upward. And you can do this with any function, right? Any function, no matter how ugly it is. Okay. Now, we're going to talk about quickly right now. How do I tell if it's a maximum or a minimum value? This is, I think, this will be the last part because we're running out of time. How do you tell if something's a max or minimum? By looking at it, by always hoping we know what the graph looks like. And here is what I'm going to say instead. Our derivative led us to 6x plus 2. That's our y prime. Okay? That's the slope for the whole graph. And if I went ahead and graphed 3x squared plus 2x squared, that's going to cost me a lot of work. Instead, let me draw you 2 ideas. If something is a maximum, okay? If something is a maximum, let's say the slope here is 0. You guys cool? That's 0. What is the slope on the left side of that critical point? Is the slope positive or negative? The slope is
Positive.
positive, right? And on the right side, the slope must be negative. The way you know something is the absolute maximum is reading from right to left. The slope goes from a positive to a negative. Now look at my image. Can you guys see my video? Look at my hand. It goes from a positive to a negative, right? Now everyone, use your left hand and do the same thing. Go from a positive to a negative. So if I go from a positive to a negative, you know it's a max. right? On the AP test, if you guys all start doing that at the same time, they'll think we're a little cult, but left to right, absolute maximum. What if it's a minimum? Here's my critical point. The slope goes from a negative to a positive, right? So using my left hand, because I read from right to left in America, the slope goes negative to a positive. So if I see a slope go from a negative to a positive, I know the critical point is going to be minimum. Now, here's the cool part. We know that, so this is what I do. This is what I recommend you guys to do. Draw a easy, brief number line. At negative 1/3, we said this was going to be 0. Just go ahead and write 0 on top. People don't do this, but I do it. I try to tell kids to do this. We know there's a critical point at negative 1/3. If you pick any number to the right of that, okay, because at negative 1/3, this would be 0. Plug in negative 1/3, it'll be 0. But if I plug in 1, 2, 3, 4, 5, is this y prime going to be positive or negative? If I plug in 1, if I plug in 2, if I plug in 3,
Positive.
positive. Did it really cost you that much brain power to figure that out? No. How about on the left? What if I plug in negative 1, negative 2, negative 3? Negative 1, negative 2, negative 3. Would that be positive or negative? Negative.
Negative.
So what is going on with the slope? The slope goes from a negative, 0, positive. Or if you want to draw this like you're a robot, negative, 0, positive. That's a minimum. We can tell any graph is a local min or local max by just talking about its slope. If the slope changes from a negative, 0 to a positive, that's a minimum. There are some parts that this fails at, and it tells you it's neither. If I draw you a graph that looks like this, the slope here could actually be 0. It could have just stopped for a moment. An x cubed does this. The slope is positive to positive. Does a graph that goes from a positive to a positive, is that a max? No, it's just a stopping point. And what we realize that a maximum must have a change of slope, a change in sign from a positive to a negative. We know this is a max. If the slope changes in sign from a negative to a positive, we know it's a minimum. Now, if I give you another problem, let's do another stupid problem. Y is equal to negative 2x squared minus 4x. Okay, let's just do this problem quickly. Find me the critical point first, and then tell me if it's a maximum or minimum. Critical point, then max or min. Okay, so go ahead and take the derivative. And then set that to 0. Right? And so we have a critical point at negative 1. If you want, you can plug it back in to find your y value. You can do that, sure. But the next part is, this is the easiest part in the world. Is it a max or a min? At negative 1, we know the slope. We know our y prime value is 0. But what about if I plug in a number bigger than that? Plug in 0, plug in 1, plug in 2, plug in 3. The slope is negative for all those values. You don't have to be specific. The point is that it's going to be negative forever. How about on the left side? If I plug in negative 2, negative 3, negative 4, that forces this to be a positive. A slope changes from a positive, 0, negative. We can automatically tell if that's a max or min. Is it a max or min, folks?
It's a max.
That's a max. And you can see, I climbed, I stopped, and then I came back down the hill. And we were able to figure that out without having to graph this graph. So for this
Can't
problem,
you can just see because of the negative sign in front, right?
you could. But what if this was x cubed? What if this was a sine? What if this was a square root? What if this was changing depending on what part the critical point was? The point is that what if I give you a graph that looks like this, right? We can see critical points happening here. Let's say the critical point is 2 and 4. So you got x is 2 and x equals to 4. So we can do our dumb graph without having to graph anything. Whoops. Here is 2, here is 4. And if I plug in the slopes go from a positive to a negative to a positive. Okay, slope is positive, 0, negative, 0, positive. And these are all done with numbers, no graphing, straight numbers. So at critical point 2, is that a max or min? Positive, 0, negative. That's a max. At 4, negative, 0, positive, that's a min. We can automatically tell that. Whether it's an absolute, we don't know. We would have to do more work. We would have to then compare to all the other critical points and the endpoints. That's something we'll talk about a little bit later. Okay. So that's it for today, at least.